The truth is out there, and so is the future. Welcome to Genii Cafe, where we explore the strange, the powerful, and the unexplained world of generative AI. With your host Nico Peters, and in each episode, we'll uncover how artificial intelligence is reshaping our reality, pushing the boundaries of creativity, and challenging everything we know. Are we witnessing the dawn of a new era, or playing with forces we can't control? Stay tuned and prepare yourself to venture beyond the edge of innovation, where technology meets the unknown.
Neural networks are a cornerstone of modern artificial intelligence, drawing inspiration from the human brain to process data in complex ways. By mimicking the functionalities of neurons and synapses, neural networks empower computers to make sense of intricate patterns and relationships within data. Essentially, neural networks are composed of layers of nodes, or neurons, each layer connected by weighted edges. These networks can be shallow with a few layers, or deep with dozens or even hundreds of layers, often referred to as deep learning networks. It's this depth that allows them to solve problems that were once deemed impossible. So what makes neural networks so vital in today's tech landscape? Let's explore a few reasons why they're pivotal autonomous systems, from self-driving cars to drones. Neural networks enable machines to perceive their environment and make quick decisions. Natural language processing, they power language models, allowing computers to understand and generate human language more naturally than ever before. Image and speech recognition, they enhance the accuracy of facial recognition and speech to text technologies, making these tools more reliable and widespread. Healthcare innovations, neural networks aid in diagnosing diseases from medical images, predicting patient outcomes, and personalizing treatment plans. Moreover, businesses leverage neural networks to optimize logistics, pricing, and customer service, driving efficiency and enhancing user experiences. As we delve deeper into this blog, you'll see how neural networks evolved starting from their inception. This evolutionary journey not only underscores their significance, but also highlights the remarkable breakthroughs that have been achieved due to their development. Let's explore how it all began. The foundation of neural networks was laid with the introduction of perceptrons, developed by Frank Rosenblatt in the 1950s and 1960s. Perceptrons marked a significant milestone in the journey towards artificial intelligence. The perceptron was designed as a type of artificial neuron and was intended to simulate how humans process visual data. Its architecture was inspired by biological neurons, and it aimed to replicate a simplified version of how the human brain would function. The perceptron operated on the basic principle of taking multiple binary inputs and processing them to produce a single binary output. Rosenblatt's perceptron was significant for several reasons. It was one of the first models to successfully demonstrate the concept of machine learning, and it illustrated the potential of machines to learn from their surroundings and experiences. One of the main structural features of the perceptron is its ability to adjust weights based on inputs and the associated error in prediction. This ability enabled the perceptron to improve its output over time, a foundational concept in modern neural networks known as learning or training. Despite its promise, the perceptron faced several limitations. It was only capable of solving linearly separable problems, prompting criticism, leading to a setback in initial neural network research. This limitation was outlined in Marvin Minsky and Seymour Papert's work, which subsequently halted progress in this field for a decade. Nevertheless, the development of perceptrons was crucial. Not only did they demonstrate the feasibility of machine learning, but they also laid the groundwork for future advancements in neural networks. The journey of neural network evolution remained dormant until new ideas breathed fresh life into the field. In the early stages of neural network development, while perceptrons offered promise, they encountered a significant bottleneck: the inability to solve nonlinear problems. This limitation stifled their application scope and potential for advancement. However, the introduction of backpropagation in the 1980s marked a revolutionary in neural network development. Backpropagation, short for backward propagation of errors, is a pivotal learning algorithm. It was introduced to address the limitations of single-layer perceptrons by enabling multi-layer networks to adjust their weights more effectively. The brilliance of backpropagation lies in its ability to systematically minimize the error of the entire network by propagating the error backward from output to input layers. This method uses a technique called gradient descent, a mathematical optimization strategy. It computes the gradient of the loss function with respect to each weight by isolated examination, adjusting them to achieve the minimal error within the network. This optimization allows networks to learn and refine complex patterns and relationships within datasets. The introduction of backpropagation invigorated neural networks, allowing for the training of deep structures which were previously impossible due to computational constraints. This advancement shifted neural networks from theoretical exploration to practical and robust tools suitable for handling real-world problems. Moreover, backpropagation catalyzed subsequent research and innovation in neural networks, encouraging the development of more sophisticated architectures. This era saw increased exploration into more complex forms of neural networks, eventually paving the way for modern advancements, such as convolutional neural networks, which have had a profound impact on image processing. As we venture into the realm of image processing, one cannot overlook the profound impact of convolutional neural networks, or CNNs. These remarkable networks have reshaped how we understand and interpret visual data. Let's delve into their inception and the breakthroughs they introduced to the world of image processing. At their core, CNNs are designed to automatically and adaptively learn spatial hierarchies of features from images. This learning capability is achieved through several layers of convolutions, pooling, and other processing nodes. Essentially, CNNs extract features from images, enabling machines to perceive visual data as humans do. One might wonder, how have CNNs truly revolutionized image processing? Well, consider the prior limitations when machines attempted to interpret images. Simple edge detection and basic pattern recognition were once at the forefront. But CNNs introduced a paradigm shift by solving complex image classification challenges with unprecedented accuracy. Modern applications of CNNs are incredibly diverse and pervasive, from facial recognition on our smartphones to the sophisticated image analysis involved in autonomous vehicles. CNNs form the backbone of these advancements. Moreover, CNNs are not limited to just identifying objects. They have been pivotal in enhancing medical imaging by aiding in diagnostics and treatment plans. In the field of entertainment, they are used to generate compelling visual effects and aid in the development of virtual reality experiences. Do these capabilities hint at the potential expansion to other domains of neural network applications? Absolutely. While CNNs primarily transform how we engage with images, other architectures like the recurrent neural networks open doors to processing sequences of data, which we will explore next. But for now, let's acknowledge convolutional neural networks have undeniably set a new benchmark in computational vision. Recurrent neural networks, or RNNs, emerge as vital tools for managing sequential data, a crucial element in the world of data processing. So what exactly are RNNs, and why are they important for tasks like language processing and time series analysis? At their core, RNNs are designed to recognize patterns in sequences of data, from simple to complex patterns. The architecture of RNNs allows them to maintain a memory of the previous inputs, thus making them well suited for tasks that require sequential processing. Consider language processing. Unlike images, where the spatial arrangement is critical, language relies on the sequence of words to convey meaning. RNNs excel here by storing information about previous words in the sequence, allowing them to predict the next word or translate text from one language to another efficiently. Another essential application of RNNs is in time series analysis. Whether it's stock market predictions or weather forecasting, time series data involves observations at successive points in time. RNNs can analyze these sequences by considering the temporal dependencies in the data, aiding in predicting future outcomes based on historical trends. Despite their advantages, RNNs are not without their challenges. They can struggle with longer sequences due to issues like vanishing gradients. However, advanced variants like long short-term memory, less-sum networks, and gated recurrent units, GRUs, have been developed to address these limitations, further enhancing the power of RNNs. In summary, RNNs have carved out a niche in handling sequential data by understanding the dependencies that are inherent in such information streams. In the evolution of neural networks, recurrent architectures provide powerful methods to unlock insights from data bound by temporal or sequential patterns. Deep learning's trajectory has profoundly transformed the landscape of artificial intelligence, building on earlier concepts of neural networks and ushering them into a new era. At its core, deep learning leverages multi-layered neural networks that resemble the intricacies of the human brain more closely than ever before, enabling the processing of vast amounts of data with unprecedented precision. One of the main catalysts for the rise of deep learning has been the increase in computational power, particularly through the utilization of GPUs, which greatly accelerated the training process of complex models. This advancement allowed for more layers or depths to be added to neural networks, thus the term deep learning. Additionally, frameworks such as TensorFlow and PyTorch have democratized access to sophisticated deep learning tools, allowing researchers and developers worldwide to contribute to and benefit from the collective effort. The open-source nature of these frameworks fueled innovation and rapid prototyping, further expanding the possibilities and applications of deep learning. Deep learning has achieved remarkable successes in various domains, transcending traditional boundaries. Whether it's advancements in natural language processing, where tasks like translation and context understanding have seen considerable improvements, or in computer vision, where image recognition has become exceptionally more accurate, deep learning's impact is undeniable. However, with great power comes significant challenges. Deep learning models often require large data sets and substantial computational resources, which can limit accessibility for some applications. There's also the challenge of black box models, where understanding the decision-making process is elusive, posing questions around accountability and reliability. Despite these challenges, the deep learning revolution continues to drive innovation and expand the horizons of what neural networks can achieve, leading us to a new chapter in neural network evolution. As we continue our journey through the history of neural networks, one of the most notable landmarks is the image milestone. The introduction of ImageNet in 2009 by Fei-Fei Li and her team transformed the field of visual recognition, serving as a pivotal moment that vastly influenced the development and performance of neural networks. ImageNet is a large-scale visual database designed for use in visual object recognition software research. With over 14 million images, it covers thousands of categories of everyday objects. This enormous dataset enabled researchers to train systems to recognize a wide array of objects, becoming a crucial asset for deep learning. The breakthrough moment came in 2012 with the annual ImageNet Large-Scale Visual Recognition Challenge. The convolutional neural network, CNN, called AlexNet, and shocked the world with its top 5 error rate of just 15.3%, a significant reduction from the 26.1% error rate of the runner-up. This feat demonstrated the true potential of deep learning and CNS, as they could outperform traditional machine learning methods by a wide margin. ImageNet's milestone experience showcased several crucial advances. Scale and diversity provided a rich dataset that covers broad categories, which pushed the limits of image recognition capabilities. CNNs in action. AlexNet's success highlighted the efficiency of convolutional neural networks for large-scale image processing tasks. Hardware and software synergy. The use of GPUs significantly accelerated the training process, illustrating the importance of high-performance computing deep learning. This milestone served not just as a turning point for computer vision, but also as a catalyst that inspired further innovations and exploration across the field of artificial intelligence. With ImageNet, neural networks began not only to see but to understand the complexities within visuals, setting the stage for future advancements. The journey of neural networks took another pivotal turn with the advent of AlphaGo, a breakthrough that highlighted AI's proficiency in mastering intricate decision-making tasks. Developed by DeepMind, AlphaGo is an AI program designed specifically to play the ancient and notoriously complex game of Go. This project was not just about playing a game, but solving a problem that had befuddled engineers and AI experts for decades. What set AlphaGo apart was its ability to evaluate millions of positions and potential moves on the Go board, a task that was considered insurmountable by traditional AI methodologies. The program utilized a combination of deep neural networks and reinforcement learning, enabling it to achieve an astonishing level of strategic planning and intuition. This was vividly demonstrated when AlphaGo defeated world-renowned Go champion Lee Sedol in 2016, a match that was considered a landmark event in AI history. AlphaGo's architecture incorporated advanced learning techniques whereby it learned from millions of games, both historical human matches and simulations. The efficacy of its neural networks was enhanced by training on a dataset filled with expert-level games. After training, it could determine the optimal moves through a sophisticated assessment of the board status at any given point. This victory was not just about beating a human champion, but illustrated the growing capability of AI to tackle tasks requiring a deep understanding of context and future prediction. AlphaGo opened avenues into how AI could be used for other strategic games and real-world problem-solving scenarios, setting a precedent for AI in tasks requiring high-level decision-making skills. With AlphaGo's success, the perception of AI shifted significantly. It wasn't just confined to data analysis and number crunching. It showed the potential to delve into realms demanding creativity and strategy. This breakthrough led to more interest and research into how neural networks could transform decision-making processes beyond the gaming world, clearing the path for future innovations in AI strategies. Building on the theme of neural networks revolutionizing complex tasks, let's dive into the world of natural language processing, NLP, with a spotlight on BERT. Short for bidirectional encoder representations from transformers, BERT represents a massive leap forward for NLP applications and understanding linguistic nuances. For BERT, language models struggle to truly grasp context, often resulting in misunderstandings, disparate translations. However, BERT introduced a remarkably effective way of processing language by considering the context of words in both directions. This bidirectional approach allows BERT to understand the intricacies of human language like never before. How did BERT achieve this breakthrough? By pre-training with double-sided context in a transformer model and fine-tuning on a variety of language tasks. This method enabled it to excel at tasks like question answering and sentence prediction with insights akin to human comprehension. Unlike previous NLP models that relied heavily on directory word, directive attention mechanism allows it to focus dynamically on different parts of a sentence. The result, a more nuanced, flexible understanding of context and meaning. Essentially, BERT processes language as fluidly as humans do. The implications for industries ranging from customer service to healthcare are enormous. For instance, BERT-powered chatbots can comprehend queries more accurately, leading to more efficient and satisfactory customer interactions. In the medical field, BERT can assist in parsing complex patient inputs, supporting better diagnostics. By transforming natural language processing, BERT has set a new standard, leading to more intuitive and context-aware AI systems. As we embrace these fascinating advances in NLP, it's important to note that navigating the development of neural networks isn't without its challenges. Let's explore those challenges next. As we navigate the intricate landscape of neural network development, it's crucial to address the formidable challenges these technologies still face. Notably, two of the most significant obstacles are computational cost and the sheer volume of data required for effective training. The computational cost associated with training advanced neural networks can be staggering. These costs are primarily due to the need for extensive hardware resources like powerful GPUs and TPUs, which can be prohibitively expensive for many organizations. This issue isn't just about finances, it also involves significant time investment, as training complex models can take days or even weeks to complete. Then there's the challenge of data requirements. Most neural networks, especially deep learning models, necessitate massive datasets to deliver accurate results. However, obtaining, cleaning, and labeling such large amounts of data can be daunting, often requiring substantial manpower or automated solutions that may not be accessible to every developer or company. Furthermore, the problem of data quality arises. Even with large datasets, if the data isn't of high quality, free from bias, errors, or inconsistencies, the performance is poor. This necessitates a rigorous process of data pre-processing and validation, further complicating the development cycle. Apart from these logistical concerns, there's an overarching need for expertise. Building these systems requires not only a profound understanding of machine learning principles, but also a cross-disciplinary knowledge base that spans mathematics, programming, and domain-specific insights. Despite these challenges, progress continues, propelled by ongoing research and innovation aimed at addressing these barriers. As neural networks evolve, enhancements in algorithms, optimization techniques, and accessible high-performance computing solutions hint at a gradually improving landscape. This paves the way for discussing what lies ahead for neural networks, hinting at an exciting future that beckons innovation. As we explore what's on the horizon for neural networks, it's clear that innovation is key to extending their capabilities while addressing the challenges they've faced. One prominent area of research is the reduction of computational costs. With the increasing complexity of models, the demand for processing power and energy consumption has skyrocketed. Researchers are now focusing on creating more efficient architectures. Techniques such as model pruning, quantization, and knowledge distillation are being investigated to reduce the size and resources required without compromising performance. While efficiency is crucial, it's equally important to enhance the interpretability of neural networks. Traditionally, these models have been described as black boxes due to their complex and opaque decision-making processes. Enhancing transparency not only helps in understanding and trusting the model outputs, but also aids in fine-tuning them. Current efforts are directed towards developing visualization tools, interpretable algorithms, and frameworks that can offer insights into how networks reach their conclusions. Another key focus area is the democratization of neural network technology. Making this technology accessible through open source libraries and platforms empowers a broader community of developers and researchers to innovate in this space. The emphasis is on lowering entry barriers and fostering inclusive participation, which will likely spur a faster evolution of ideas and solutions. In essence, the future of neural networks is about making them more efficient, understandable, and accessible. As we look ahead, these advancements will play a vital role in unlocking new applications and capabilities, leading us into an exciting era of AI-driven possibilities. As we stand at the close of our exploration into the intricate world of neural networks, it's intriguing to reflect on how far this technology has come and the myriad of possibilities that lie ahead. We've traversed through the fascinating history, dissected groundbreaking architectures, and charted the incredible transformations in various industries powered by these marvels of computational prowess. Neural networks have fundamentally altered how we approach problem solving across an array of fields, from healthcare and finance to entertainment and autonomous systems. Their ability to learn and adapt makes them indispensable in navigating complex challenges that traditional algorithms struggle to manage. The iterative journey of neural networks has been marked by innovation and the relentless pursuit of improving precision and performance. As we've seen, the continued expansion in data generation alongside the advancements in computational resources has been instrumental in propelling neural networks to new heights. They have become more efficient and powerful, unraveling insights that were once locked away, hidden beneath layers of complexity. Reflecting on the spectrum of neural networks from perceptrons to deep learning architectures, we recognize their profound impact in transforming industries. These advancements have not only improved existing processes but opened the door to entirely new paradigms and products. As we conclude, it's essential to acknowledge both the capabilities and the responsibilities that come with this powerful tool. Ethical considerations and responsible deployment must be at the forefront of ongoing development to ensure that neural networks benefit society as a whole. In summary, our journey through the evolution of neural networks reveals a narrative rich with both challenges and breakthroughs. These systems stand as testaments to human ingenuity and a beacon for future innovations. As technology continues to evolve, let us remain both curious and vigilant, pushing the boundaries of what's possible while maintaining a steadfast commitment to doing so ethically.